is when we remove all the circles, and the points themselves are 6 trivial clusters. Removing the circles in decreasing order of their size produces a collection of different clusterings, each with a larger number of clusters. Compare these circles to a dendrogram, which shows explicitly the hierarchy of the clusters. Points A through F are arranged along the x-axis, and the y-axis represents the distance between the clusters. We'll talk more about that presently. At the bottom of the graph, where y equals 0, each point is in a separate cluster. As y increases, different groupings of clusters fall within the distance constraint. First A and C are clustered together, then B and E are merged. Then the BE cluster is merged with D, and so on, until all clusters are merged at the top. It should now be apparent that hierarchical clustering doesn't just create a clustering, or a single set of groups of objects. It creates a collection of ways to group the points. To picture this clearly, imagine clipping the dendrogram with a horizontal line, ignoring everything above the line. As the line moves downward, we get different clusterings with increasing numbers of clusters. Clipping the dendrogram near the top might leave us with 2 different groups. The singleton point F, which stood apart from the rest of the points on the initial 2-dimensional plane, and the group containing all of the other points. If we move the horizontal line lower and clip the dendrogram there, we may be left with 3 groups below the line: AC, BED, and F. Intuitively, the clusters make sense. F is still off by itself, B, E, and D form a relatively close group, and A and C form a very close group. An advantage of hierarchical clustering is that it allows the data analyst to see the groupings, the landscape of data similarity, before deciding on the number of clusters to extract. As shown by the horizontal dashed lines, the diagram can be cut across at any point to give any desired number of clusters. Note also that once 2 clusters are joined at one level, they remain joined in all higher levels of the hierarchy. Hierarchical clusterings generally are formed by starting with each node as its own cluster. Then, clusters are merged iteratively until only a single cluster remains. The clusters are merged based on the similarity or distance function that is chosen. So far, we have discussed distance between instances. For hierarchical clustering, we need a distance function between clusters, considering individual instances to be the smallest clusters. This is sometimes called the linkage function. So, for example, the linkage function could be the Euclidean distance between the closest points in each of the clusters, which would apply to any 2 clusters. Note: dendrograms. 2 things can usually be noticed in a dendrogram. Because the y-axis represents the distance between clusters, the dendrogram can give an idea of where natural clusters may occur. For example, a relatively long distance between 2 clusters suggests that a segmentation of the data, perhaps yielding 3 clusters, might be a good division. Also, whenever a single point merges high up in a dendrogram, this is an indication that the point seems different from the rest, which we might call an outlier, and want to investigate it. Returning to our example from the outset of the chapter, consider a dendrogram of single malt Scotch whiskies clustered using the methodology described by Lapointe and Lejeune. By clipping the dendrogram, we can obtain any number of clusters we would like. So, going back to Foster's new favorite single malt, Bunnahabhain, the dendrogram would show that most of its nearest neighbors, such as Tullibardine and Glenglassaugh, cluster near it in the hierarchy. Note, however, that the clusters may not correspond exactly to the similarity ranking earlier. While the whiskies we found are the most similar to Bunnahabhain, some of them are more similar to other whiskies in the dataset, so they are clustered with these closer neighbors before joining Bunnahabhain. Interestingly, from the point of view of whiskey classification, the groups of single malts resulting from this taste-based clustering do not correspond neatly with regions of Scotland, the basis of the usual categorizations of Scotch whiskies. There is a correlation, however, as Lapointe and Lejeune point out. So, Instead of simply stocking the most recognizable scotches or a few Highland, Lowland, and Islay brands, our specialty shop owner could choose to stock single malts from the different clusters. Alternatively, one could create a guide to Scotch whiskies that might help single malt lovers to choose whiskies. For example, since Foster loved the Bunnahabhain recommended to him by his friend at the restaurant the other night, he can use the clustering to find a set of other, most similar whiskies. Note that the most unusual tasting single malt in the data, in this case Altmore, would appear at the very top of the dendrogram, making it the last whiskey to join any others. Nearest neighbors revisited. Clustering around centroids. Hierarchical clustering focuses on the similarities between the individual instances and how similarities link them together. A different way of thinking about clustering data is to focus on the clusters themselves, the groups of instances. The most common method for focusing on the clusters themselves is to represent each cluster by its cluster center, or centroid. The centroid is not necessarily one of the instances. It is the geometric center of a group of instances. This same idea applies to any number of dimensions, as long as we have a numeric instance space and a distance measure. Of course, we can't visualize the clusters so nicely, if at all, in high-dimensional space. The most popular centroid-based clustering algorithm is called k-means clustering, and the main idea behind it deserves some discussion, as k-means clustering is mentioned frequently in data science. In k-means, the means are the centroids, represented by the arithmetic means, averages, of the values along each dimension for the instances in the cluster. The k is simply the number of clusters that one would like to find in the data. Unlike hierarchical clustering, k-means starts with a desired number of clusters k. To compute the centroid for a cluster, we average all the x values of the points in the cluster to form the x-coordinate of the centroid, and average all the y values to form the centroid's y-coordinate. Generally, the centroid is the average of the values for each feature of each example in the cluster. The k-means algorithm for finding the cluster is simple and elegant, and therefore is worth mentioning. The algorithm starts by creating k initial cluster centers, usually randomly, but sometimes by choosing k of the actual data points, or by being given specific initial starting points by the user, or via pre-processing the data to determine a good set of starting centers. Then, the clusters corresponding to these cluster centers are formed by determining which is the closest center to each point in the dataset. Next, for each of these clusters, its center is recalculated by finding the actual centroid of the points in the cluster. And that's pretty much it. The process simply iterates. Since the cluster centers have shifted, we need to recalculate which points belong to each other. Once these are reassigned, we might have to shift the cluster centers again. The k-means procedure keeps iterating until there is no change in the clusters, or possibly until some other stopping criterion is met. There is no guarantee that a single run of the k-means algorithm will result in a good clustering. The result of a single clustering run will find a local optimum, a locally best clustering, but this will be dependent upon the initial centroid locations. For this reason, k-means is usually run many times, starting with different random centroids each time. The results can be compared by examining the clusters, more on that in a minute, or by a numeric measure such as the cluster's distortion, which is the sum of the squared differences between each data point and its corresponding centroid. In the latter case, the clustering with the lowest distortion value can be deemed the best clustering. In terms of runtime, the k-means algorithm is efficient. Even with multiple runs, it is generally relatively fast because it only computes the distances between each data point and the cluster centers on each iteration. Hierarchical clustering is generally slower, as it needs to know the distances between all pairs of clusters on each iteration, which at the start is all pairs of data points. A common concern with centroid algorithms such as k-means is how to determine a good value for k. One answer is simply to experiment with different k values and see which ones generate good results. Since k-means is often used for exploratory data mining, the analyst must examine the clustering results anyway to determine whether the clusters make sense. Usually, this can reveal whether the number of clusters is appropriate. The value for k can be decreased if some clusters are too small and overly specific, and increased if some clusters are too broad and diffuse. For a more objective measure, the analyst can experiment with increasing values of k and graph various metrics, sometimes obliquely called indices, of the quality of the resulting clusterings. As k increases, the quality metrics should eventually stabilize or plateau, either bottoming out if the metric is to be minimized or topping out if maximized. Some judgment will be required, but the minimum k where the stabilization begins is often a good choice. The Wikipedia article, Determining the Number of Clusters in a Dataset, describes various metrics for evaluating sets of candidate clusters. Example: clustering business news stories. As a concrete example of centroid-based clustering, consider the task of identifying some natural groupings of business news stories released by a news aggregator. The objective of this example is to identify, informally, different groups of news stories released about a particular company. This may be useful for a specific application. For example, to get a quick understanding of the news about a company without having to read every news story. To categorize forthcoming news stories for a news prioritization process, or simply to understand the data before undertaking a more focused data mining project, such as relating business news stories to stock performance. For this example, we chose a large collection of text news stories, the Thomson Reuters Text Research Collection, a corpus of news stories created by the Reuters news agency and made available to researchers. The entire corpus comprises approximately 1,800,000 news stories from January of 2008 through February of 2009, 14 months. To make the example tractable but still realistic, we're going to extract only those stories that mention a particular company. In this case, Apple. Data preparation. For this example, it is useful to discuss data preparation in a little detail, as we will be treating text as data, and we have not previously discussed that. Chapter 10 contains more details on mining text. In this corpus, large companies are always mentioned when they are the primary subject of a story, such as in earnings reports and merger announcements. But they are often mentioned peripherally in weekly business summaries, lists of active stocks, and stories mentioning significant events within their industry sectors. For example, many stories about the personal computer industry mention how HP's and Dell's stock prices reacted on that day, even if neither company was involved in the event. For this reason, we extracted stories whose headlines specifically mentioned Apple, thus assuring that the story is very likely news about Apple itself. There were 312 such stories, but they covered a wide variety of topics. Prior to clustering, the stories underwent basic web text processing, with HTML and URLs stripped out and the text case normalized. Words that occurred rarely, in fewer than 2 of the documents, or too commonly, in more than 50% of the documents, in the corpus were eliminated, and the rest formed the vocabulary for the next step. Then, each document was represented by a numeric feature vector using term frequency times inverse document frequency, TF-IDF scores, scoring for each vocabulary word in the document. TF-IDF scores represent the frequency of the word in the document, penalized by the frequency of the word in the corpus. TF-IDF is explained in detail later in Chapter 10. The similarity metric used was cosine similarity, introduced in Chapter 6. It is commonly used in text applications to measure the similarity of documents. The news story clusters. We chose to cluster the stories into 9 groups, so k equals 9 for k-means. we present a description for each cluster, along with a sample headline from that cluster. It is important to remember that the entire news story was used in the clustering, not just the headline. Cluster 1 contains analyst announcements concerning ratings changes and price target adjustments. Sample headline: RBC raises Apple price target to $200 from $190. Keeps outperform rating. Cluster 2 contains stories about Apple's stock price movement during and after each day of trading. Sample headline: Apple shares rise on optimism over iPhone demand. Cluster 3 contains stories about Steve Jobs, Apple's charismatic former CEO, and his struggle with pancreatic cancer, especially speculation on how well Apple would continue without him. Sample headline: Analysis: Apple's success linked to more than just Steve Jobs. Cluster 4 contains various Apple announcements and releases. Sample headline: Apple introduces iPhone, push email software. Cluster 5 contains stories about the iPhone and deals to sell iPhones in other countries. Sample headline: Megaphone says to sell Apple iPhone in Russia. Cluster 6 contains stories reporting on stock price movements outside of normal trading hours, known as before and after the bell. Sample headline: Before the bell, Apple inches up on broker action. Cluster 7 contains little thematic consistency, featuring stories with headlines ranging from Analysis: Less cheer as Apple confronts an uncertain 2009, to Take a look, Apple Macworld Convention, to Apple's Jobs finishes speech announcing movie plan. Cluster 8 contains stories on iTunes and Apple's position in digital music sales. Sample headline: Apple iTunes grows to number 2 U.S. music retailer. And finally, Cluster 9 contains Reuters news stories called news briefs, which are usually just a few itemized lines of very terse text. The contents of these news briefs varies, but because of their very similar form, they clustered together. Some of these clusters are interesting and thematically consistent, while others are not. Some are just collections of superficially similar text. There's an old cliché in statistics: correlation is not causation, meaning that just because two things co-occur doesn't mean that one causes another. A similar caveat in clustering could be: syntactic similarity is not semantic similarity. Just because two things, particularly text passages, have common surface characteristics doesn't mean they're necessarily related semantically. We shouldn't expect every cluster to be meaningful and interesting. Nevertheless, clustering is often a useful tool to uncover structure in our data that we did not foresee. Clusters can suggest new and interesting data mining opportunities. Understanding the results of clustering. Once we have formulated the instances and clustered them, then what? As we mentioned earlier, the result of clustering is either a dendrogram or a set of cluster centers plus the corresponding data points for each cluster. How can we understand the clustering? This is particularly important because clustering often is used in exploratory analysis. So the whole point is to understand whether something was discovered, and if so, what? How to understand clusterings and clusters depends on the sort of data being clustered and the domain of application. But there are several methods that apply broadly. We have explored some of them already. Consider our whiskey example. Our whiskey researchers, Lapointe and Lejeune, cut their dendrogram into 12 clusters. Thus, to examine the clusters, we simply can look at the whiskeys in each cluster. That seems rather easy, but what is it about the application that allows relatively easy examination of the clusters? We might think, well, there are only a small number of whiskeys in total. That allows us to actually look at them all. This is true, but it actually is not so critical. If we had massive numbers of whiskeys, we could still have sampled whiskeys from each cluster to show the composition of each. The more important factor to understanding these clusters, at least for someone who knows a little about single malts, is that the elements of the cluster can be represented by the names of the whiskeys. In this case, the names of the data points are meaningful in and of themselves and convey meaning to an expert in the field. This gives us a guideline that can be applied to other applications. For example, if we are clustering the customers of a large retailer, probably a list of the names of the customers in a cluster would have little meaning. So, this technique for understanding the results of clustering would not be useful. On the other hand, if IBM is clustering business customers, it may be that the names of the businesses, or at least many of them, carry considerable meaning to a manager or member of the sales force. What can we do in cases where we cannot simply show the names of our data points, or for which showing the names does not give sufficient understanding? Well, for our whiskey clusters, for example, we could include more information on the clusters, not just the name of each whiskey, but also the best rated or best selling whiskey of the cluster, the average color, the average dryness, and more. Listing the exemplar member of each class, in this case, the best rated or best selling whiskey, could be especially useful when there are massive numbers of instances in each cluster, so randomly sampling some may not be as telling as carefully selecting exemplars. However, this still presumes that the names of the instances are meaningful. Our other example, clustering the business news stories, shows a slight twist on this general idea. Show exemplar stories and their headlines, because there the headlines can be meaningful summaries of the stories. By listing the average characteristics of the members of a cluster, such as the average color, dryness, and so on of the whiskeys, we are essentially showing the cluster centroid. Showing the centroid can be applied to any clustering. Whether it is meaningful depends on whether the data values themselves are meaningful. Stepping back, solving a business problem versus data exploration. We have now heard various examples of our fundamental concepts of data science in action. You may have realized that the clustering examples seem somehow different from the predictive modeling examples, and even the examples of finding similar objects. Let's examine why. In our predictive modeling examples, as well as our examples of using similarity directly, we focused on solving a very specific business problem. As we have emphasized, one of the fundamental concepts of data science is that one should work to define as precisely as possible the goal of any data mining. Recall the crisp data mining process introduced in Chapter 2, which comprises business and data understanding, data preparation, modeling, evaluation, and deployment. We should spend as much time as we can in the business understanding data understanding mini-cycle until we have a concrete, specific definition of the problem we are trying to solve. In predictive modeling applications, we are aided by our need to define the target variable precisely, and we will discover in Chapter 7 that we can get more and more precise about defining the problem as we get more sophisticated in our understanding of data science. In our similarity matching examples, again, we had a very concrete notion of what exactly we were looking for. We want to find similar companies to optimize our efforts, and we will define specifically what it means to be similar. We want to find similar whiskeys, specifically in terms of taste, and we again work to gather and represent the data so that we can find exactly these. Later in the book, we will discuss how we often expend considerable effort applying data science frameworks to decompose business problems into multiple, well-defined components, each of which we might apply data science methods to solve. However, not all problems are so well defined. What do we do when in the business understanding phase we conclude we would like to explore our data, possibly with only a vague notion of the exact problem we are solving? The problems to which we apply clustering often fall into this category. We want to perform unsupervised segmentation, finding groups that naturally occur, subject of course to how we define our similarity measures. For the sake of discussion, let's simplify by separating our problems into supervised, such as predictive modeling, and unsupervised, such as clustering. The world is not so cut and dried, and just about any of the data mining techniques we have presented could be used for data exploration. but the discussion will be much clearer if we do simply separate into supervised versus unsupervised. There is a direct trade-off in where and how effort is expended in the data mining process. For the supervised problems, since we spent so much time defining precisely the problem we were going to solve, in the evaluation stage of the data mining process, we already have a clear-cut evaluation question. Do the results of the modeling seem to solve the problem we have defined? For example, if we had defined our goal as improving prediction of defection when a customer's contract is about to expire, we could assess whether our model has done this. In contrast, unsupervised problems often are much more exploratory. We may have a notion that if we could cluster companies, news stories, or whiskeys, we would understand our business better, and therefore be able to improve something. However, we may not have a precise formulation. We should not let our desire to be concrete and precise keep us from making important discoveries from data. But there is a trade-off. The trade-off is that for problems where we did not achieve a precise formulation of the problem in the early stages of the data mining process, we have to spend more time later in the process in the evaluation stage. For clustering specifically, it often is difficult even to understand what, if anything, the clustering reveals. Even when the clustering does seem to reveal interesting information, it often is not clear how to use that to make better decisions. Therefore, for clustering, additional creativity and business knowledge must be applied in the evaluation stage of the data mining process. Ira Heimowitz and Henry Schwartz show a concrete example of how clustering was used to improve decisions about how to set credit lines for new credit customers. They clustered existing GE Capital customers based on similarity in their use of their cards, payment of their bills, and profitability to the company. After some work, they settled on 5 clusters that represented very different consumer credit behavior. For example, those who spend a lot but pay off their cards in full each month, versus those who spend a lot and keep their balance near their credit limit. These different sorts of customers can tolerate very different credit lines. In the 2 examples, extra care must be taken with the latter to avoid default. The problem with using this clustering immediately for decision-making is that the data are not available when the initial credit line is set. Briefly, Heimowitz and Schwartz took this new knowledge and cycled back to the beginning of the data mining process. They used the knowledge to define a precise predictive modeling program. Using data that are available at the time of credit approval, predict the probability that a customer will fall into each of these clusters. This predictive model then can be used to improve initial credit line decisions. Summary. The fundamental concept of similarity between data items occurs throughout data mining. In this chapter, we first discussed a wide variety of uses of similarity, ranging from finding similar entities or objects based on their data descriptions, to predictive modeling, to clustering entities. We discussed these various uses and gave examples. A very common proxy for the similarity of 2 entities is the distance between them in the instance space defined by their feature vector representation. We presented similarity and distance computations, generally and in technical detail. We also introduced a family of methods, called nearest neighbor methods, that perform prediction tasks by calculating explicitly the similarity between a new example and a set of training examples, with known values for the target. Once we can retrieve a set of nearest neighbors, most similar examples, we can use these for various data mining tasks: classification, regression, and instance scoring. Finally, we showed how the same fundamental concept, similarity, also underlies the most common methods for unsupervised data mining, clustering. We also discussed another important concept that raises its head once we begin to look seriously at methods, such as clustering, that are employed for more exploratory data analysis. When exploring the data, especially with unsupervised methods, we usually end up spending less time at the outset in the business understanding phase of the data mining process, but more time in the evaluation stage and in iterating around the cycle. To demonstrate, we discussed a variety of methodologies for understanding the results of clusterings. Chapter 7. Decision Analytic Thinking 1. What is a good model? The fundamental concepts discussed in this chapter are careful consideration of what is desired from data science results, expected value as a key evaluation framework, and consideration of appropriate comparative baselines. The exemplary techniques are various evaluation metrics, estimating costs and benefits, calculating expected profit, and creating baseline methods for comparison. Recall from the beginning of Chapter 5, as a manager at Mega Telco, you wanted to assess whether the model my consulting firm had produced was any good. Overfitting aside, how would you go about measuring that? For data science to add value to an application, it is important for the data scientists and other stakeholders to consider carefully what they would like to achieve by mining data. This sounds obvious, so it is sometimes surprising how often it is ignored. Both data scientists themselves and the people who work with them often avoid, perhaps without even realizing it, connecting the results of mining data back to the goal of the undertaking. This may manifest itself in the reporting of a statistic without a clear understanding of why it is the right statistic, or in the failure to figuring out how to measure performance in a meaningful way. We should be careful with such a criticism, though. Often, it is not possible to measure perfectly one's ultimate goal. For example, because the systems are inadequate, or because it is too costly to gather the right data, or because it is difficult to assess causality. So, we might conclude that we need to measure some surrogate for what we'd really like to measure. It is nonetheless crucial to think carefully about what we'd really like to measure. If we have to choose a surrogate, we should do it via careful, data analytic thinking. A challenge with writing a chapter on this topic is that every application is different. We cannot offer a single evaluation metric that is right for any classification problem or regression problem, or whatever problem you may encounter. Nevertheless, there are various common issues and themes in evaluation, and frameworks and techniques for dealing with them. In this chapter, we will work through a set of such frameworks and metrics for tasks of classification, and in the following chapter, we will focus on instance scoring. For example, ordering consumers by their likelihood of responding to an offer, and class probability estimation. The specific techniques should be seen as examples demonstrating the general concept of thinking deeply about the needs of the application. Fortunately, these specific techniques do apply quite broadly. We also will describe a very general framework for thinking about evaluation, using expected value, that can cover a very wide variety of applications. As we will learn in a later chapter, it also can be used as an organizational tool for data analytic thinking generally, all the way back to problem formulation. Evaluating classifiers. Recall that a classification model takes an instance for which we do not know the class and predicts its class. Let's consider binary classification, for which the classes often are simply called positive and negative. How shall we evaluate how well such a model performs? In Chapter 5, we discussed how, for evaluation, we should use a holdout test set to assess the generalization performance of the model. But how should we measure generalization performance? Sidebar: bad positives and harmless negatives. In discussing classifiers, we often refer to a bad outcome as a positive example, and a normal or good outcome as negative. This may seem odd to you, given the everyday definitions of positive and negative. Why, for example, is a case of fraud considered positive and a legitimate case considered negative? This terminology is conventional in many fields, including machine learning and data mining, and we will use it throughout this book. Some explanation may be useful to avoid confusion. It is useful to think of a positive example as one worthy of attention or alarm, and a negative example as uninteresting or benign. For example, a medical test, which is a type of classifier, performed on a biological sample, tries to detect disease or an unusual condition by examining certain aspects of the sample. If the test comes back positive, it means the disease or condition is present. If the test is negative, there is no cause for alarm and usually no need for treatment. Similarly, if a fraud detector finds unusual activity on a customer account and decides there is cause for alarm, this is called a positive. On the other hand, negatives, accounts with only legitimate activity, are profitable, but from a fraud detection perspective, they are unworthy of attention. There are advantages to maintaining this general orientation rather than redefining the meaning of positive and negative for every domain we introduce. You can think of a classifier as sifting through a large population consisting mostly of negatives, the uninteresting cases, looking for a small number of positive instances. By convention, then, the positive class is often rare, or at least rarer than the negative class. In consequence, the number of mistakes made on negative examples, the false positive errors, may dominate, though the cost of each mistake made on a positive example, a false negative error, will be higher. Plain accuracy and its problems. Up to this point, we have assumed that some simple metric, such as classifier error rate or accuracy, was being used to measure a model's performance. Classification accuracy is a popular metric because it's very easy to measure. Unfortunately, it is usually too simplistic for applications of data mining techniques to real business problems. This section discusses it and some of the alternatives. The term classifier accuracy is sometimes used informally to mean any general measure of classifier performance. Here, we will reserve accuracy for its specific technical meaning as the proportion of correct decisions. That is, accuracy equals the number of correct decisions made divided by the total number of decisions made. This is equal to 1 minus the error rate. Accuracy is a common evaluation metric that is often used in data mining studies because it reduces classifier performance to a single number and it is very easy to measure. Unfortunately, it is simplistic and has some well-known problems. To understand these problems, we need a way to decompose and count the different types of correct and incorrect decisions made by a classifier. For this, we use the confusion matrix. The confusion matrix. To evaluate a classifier properly, it is important to understand the notion of class confusion and the confusion matrix, which is one sort of contingency table. A confusion matrix for a problem involving n classes is an n by n matrix with the columns labeled with actual classes and the rows labeled with predicted classes. Each example in a test set has an actual class label as well as the class predicted by the classifier, the predicted class, whose combination determines which matrix cell the instance counts into. For simplicity, we will deal with two class problems having 2 by 2 confusion matrices. A confusion matrix separates out the decisions made by the classifier, making explicit how one class is being confused for another. In this way, different sorts of errors may be dealt with separately. Positive and negative are at the labels at the top of the 2 by 2 confusion matrix, while yes and no are the labels on the left side of the matrix. Thus, the main diagonal from top left to bottom right contains the counts of the correct decisions. Specifically, the positive yes square contains the number of true positives, and the negative no square contains the number of true negatives. The errors of the classifier are the false positives, negative instances classified as positive, in the negative yes square, and the false negatives, positives classified as negative in the positive no square. Problems with unbalanced classes. As an example of how we need to think carefully about model evaluation, consider a classification problem where one class is rare. This is a common situation in applications because classifiers often are used to sift through a large population of normal or uninteresting entities in order to find a relatively small number of unusual ones. For example, looking for defrauded customers, checking an assembly line for defective parts, or targeting consumers who actually would respond to an offer. Because the unusual or interesting class is rare among the general population, the class distribution is unbalanced or skewed. Unfortunately, as the class distribution becomes more skewed, evaluation based on accuracy breaks down. Consider a domain where the classes appear in a 999:1 ratio. A simple rule, always choose the most prevalent class, gives 99.9% accuracy. Presumably, this is not satisfactory if a non-trivial solution is sought. Skews of 1 to 100 are common in fraud detection, and skews greater than 1 to 1 million have been reported in other classifier learning applications. Chapter 5 mentions the base rate of a class, which corresponds to how well a classifier would perform by simply choosing that class for every instance. With such skewed domains, the base rate for the majority class could be very high, so a report of 99.9% accuracy may tell us little about what data mining has really accomplished. Even when the skew is not so great, in domains where one class is more prevalent than another, accuracy can be greatly misleading. Consider again our cellular churn example. Let's say you're a manager at Mega Telco, and as an analyst, I report that our churn prediction model generates 80% accuracy. This sounds good, but is it? My coworker reports that her model generates an accuracy of 64%. That's pretty bad, isn't it? You might say, wait, we need more information about the data, and you would be exactly right to do so, and would be engaging in data analytic thinking. What do we need? Considering the line of discussion so far in this subsection, you might rightly say, we need to know what is the proportion of churn in the population we are considering. Let's say you know that in these data, the baseline churn rate is approximately 10% per month. Let's consider a customer who churns to be a positive example. So, within our population of customers, we expect a positive to negative class ratio of 1 to 9. So, if we simply classify everyone as negative, we could achieve a base rate accuracy of 90%. Digging deeper, you discover that my coworker and I evaluated on 2 different data sets. This would not be surprising if we had not coordinated our data analysis efforts. My coworker calculated the accuracy on a representative sample from the population, whereas I created artificially balanced data sets for training and testing, both common practices. Now, my coworker's model looks really bad. She could have achieved 90% accuracy, but only got 64%. However, when she applies her model to my balanced data set, she also sees an accuracy of 80%. Now it's really confusing. The bottom line is that accuracy simply is the wrong thing to measure. In this admittedly contrived example, my coworker's model, call it Model A, achieves 80% accuracy on the balanced sample by correctly identifying all positive examples, but only 60% of the negative examples. My model, Model B, does this conversely by correctly identifying all the negative examples, but only 60% of the positive examples. Let's consider these 2 models more carefully, using confusion matrices as a conceptual tool. In a training population of 1,000 customers, Model A's confusion matrix shows 500 true positives, accurate predictions of churn, and 300 true negatives, accurate predictions of no churn. There are no false positives, inaccurate predictions of churn, but 200 false negatives, inaccurate predictions of no churn. Using the same training population, Model B's confusion matrix shows 300 true positives, accurate churn predictions, 500 true negatives, accurate no churn predictions, 200 false positives, inaccurate churn predictions, and 0 false negatives, inaccurate no churn predictions. As mentioned, if the population is balanced, with a 50% churn rate, the 2 models have the same accuracy. They both correctly classify 80% of the balanced population. However, Model A often falsely predicts that customers will churn when they will not, while Model B makes opposite errors of predicting that customers will not churn when in fact they will. As such, when applied to the original unbalanced population of customers with only a 10% churn rate, Model A's accuracy declines to 64%, while Model B's rises to 96%. This is a huge change. So, which model is better? My Model B now appears to be better than A, because B seems to have greater performance on the population we care about, the 1 to 9 mix of customers we expect to see. But we still can't say for sure because of another problem with accuracy. We don't know how much we care about the different errors and correct decisions. This issue is the topic of the next section. Problems with unequal costs and benefits. Another problem with simple classification accuracy as a metric is that it makes no distinction between false positive and false negative errors. By counting them together, it makes the tacit assumption that both errors are equally important. With real-world domains, this is rarely the case. These are typically very different kinds of errors with very different costs because the classifications have consequences of differing severity. Consider a medical diagnosis domain where a patient is wrongly informed he has cancer when he does not. This is a false positive error. The result would likely be that the patient would be given further tests or a biopsy, which would eventually disconfirm the initial diagnosis of cancer. This mistake might be expensive, inconvenient, and stressful for the patient, but it would not be life-threatening. Compare this with the opposite error, a patient who has cancer, but she is wrongly told she does not. This is a false negative. This second type of error would mean a person with cancer would miss early detection, which could have far more serious consequences. These two errors are very different, should be counted separately, and should have different costs. Returning to our cellular churn example, consider the cost of giving a customer a retention incentive, which still results in departure, a false positive error. Compare this with the cost of losing a customer because no incentive was offered, a false negative. Whatever costs you might decide for each, it is unlikely they would be equal, and the errors should be counted separately regardless. Indeed, it is hard to imagine any domain in which a decision maker can safely be indifferent to whether she makes a false positive or a false negative error. Ideally, we should estimate the cost or benefit of each decision a classifier can make. Once aggregated, these will produce an expected profit, or expected benefit or expected cost, estimate for the classifier. Generalizing beyond classification. We have been using classification modeling to illustrate many data science issues concretely. Most of these issues are applicable beyond classification. The general principle we're developing here is that when we are applying data science to an actual application, it is vital to return to the question, what is important in the application? What is the goal? Are we assessing the results of data mining appropriately given the actual goal? As another example, let's apply this thinking to regression modeling rather than classification. Say our data science team has to build a movie recommendation model. It predicts how much a given customer will like a given movie, which we will use to help us provide personalized recommendations. Let's say each customer rates a movie by giving it 1 to 5 stars, and the recommendation model predicts how many stars a user will give an unseen movie. One of our analysts describes each model by reporting the mean squared error, or root mean squared error, or R squared, or whatever metric, for the model. We should ask, mean squared error of what? The analyst replies, the value of the target variable, which is the number of stars that a user would give as a rating for the movie. Why is the mean squared error on the predicted number of stars an appropriate metric for our recommendation problem? Is it meaningful? Is there a better metric? Hopefully, the analyst has thought this through carefully. It is surprising how often one finds that an analyst has not, and is simply reporting some measure he learned about in a class in school. A key analytical framework, expected value. We now are ready to discuss a very broadly useful conceptual tool to aid data analytic thinking: expected value. The expected value computation provides a framework that is extremely useful in organizing thinking about data analytic problems. Specifically, it decomposes data analytic thinking into 1. The structure of the problem, 2. The elements of the analysis that can be extracted from the data, and 3. The elements of the analysis that need to be acquired from other sources, such as business knowledge of subject matter experts. In an expected value calculation, the possible outcomes of a situation are enumerated. The expected value is then the weighted average of the values of the different possible outcomes, where the weight given to each value is the probability of occurrence. For example, if the outcomes represent different possible levels of profit, an expected profit calculation weights heavily the highly likely levels of profit, while unlikely levels of profit are given little weight. For this book, we will assume that we are considering repeated tasks, like targeting a large number of consumers or diagnosing a large number of problems, and we are interested in maximizing expected profit. The probabilities in an expected value calculation often can be estimated from the data, but the business values often need to be acquired from other sources. As we will learn in Chapter 11, data-driven modeling may help estimate business values, but usually the values must come from external domain knowledge. We now will explore the use of expected value as an analytical framework with two different data science scenarios. The two scenarios are often confused, but it is vital to be able to distinguish them. To do so, recall the difference from Chapter 2 between the mining, or induction of a model, and the model's use. Using expected value to frame classifier use. In use, we have many individual cases for which we would like to predict a class, which may then lead to an action. In targeted marketing, for example, we may want to assign each consumer a class of likely responder versus not likely responder. Then, we could target the likely responders. Unfortunately, for targeted marketing, often the probability of response for any individual consumer is very low, maybe 1 or 2%. So no consumer may seem like a likely responder. If we choose a common sense threshold of 50% for deciding what a likely responder is, we would probably not target anyone. Many inexperienced data miners are surprised when the application of data mining models results in everybody being classified as not likely responder, or a similar negative class. However, with the expected value framework, we can see the crux of the problem. Let's walk through a targeted marketing scenario. Consider that we have an offer for a product that, for simplicity, is only available via this offer. If the offer is not made to a customer, the consumer will not buy the product. We have a model, mined from historical data, that gives an estimated probability of response for any consumer whose feature vector description X is given as input. The model could be a classification tree or a logistic regression model, or some other model we haven't talked about yet. Now, we would like to decide whether to target a particular consumer described by feature vector X. Expected value provides a framework for carrying out the analysis. Specifically, let's calculate the expected benefit, or cost, of targeting consumer X. The expected benefit of targeting a consumer is the probability of response times the value of response minus the probability of no response times the value of no response. The values of response and no response need to be determined separately as part of the CRISP data mining process's business understanding step. Since a customer can only purchase the product by responding to the offer, the expected benefit of not targeting her, conveniently, is 0. To be concrete, let's say that a consumer buys the product for $200 and our product-related costs are $100. To target the consumer with the offer, we also incur a cost. Let's say that we mail some flashy marketing materials and the overall cost, including postage, is $1, yielding a value, profit, of $99 if the consumer responds. That is, buys the product. Now, what about the value to us if the consumer does not respond? We still mailed the marketing materials, incurring a cost of $1, or equivalently, a benefit of -$1. Now we are ready to say precisely whether we want to target this consumer. Do we expect to make a profit? Technically, is the expected value, profit, of targeting greater than 0? Mathematically, we find that we should target the consumer as long as the estimated probability of responding is greater than 1%. This shows how an expected value calculation can express how we will use the model. Making this explicit helps to organize problem formulation and analysis. We will return to this in Chapter 11. Now, let's move on to the other important application of the expected value framework, to organize our analysis of whether the model we have induced from the data is any good. Using expected value to frame classifier evaluation. At this point, we want to shift our focus from individual decisions to collections of decisions. Specifically, we need to evaluate the set of decisions made by a model when applied to a set of examples. Such an evaluation is necessary in order to compare one model to another. For example, does our data-driven model perform better than the handcrafted model suggested by the marketing group? Does a classification tree work better than a linear discriminant model for a particular problem? Do any of the models do substantially better than a baseline model, such as randomly choosing consumers to target? It is likely that each model will make some decisions better than the other model. What we care about is, in aggregate, how well does each model do? What is its expected value? We can use the expected value framework just described to determine the best decisions for each particular model, and then use the expected value in a different way to compare the models. If we are to calculate the expected profit for a model in aggregate, we want to aggregate all the different possible outcomes. Overall, when we decide to target consumers, what is the probability that they respond? What is the probability that they do not? What about when we do not target consumers? Would they have responded? Fortunately, as you may recall, we already have the counts necessary to calculate all these in the confusion matrix. Each outcome corresponds to one cell of the confusion matrix. For example, what is the probability associated with the particular combination of a consumer being predicted to churn and actually does not churn? That would be estimated by the number of test set consumers who fell into the confusion matrix cell of false positives, divided by the total number of test set consumers. Let's walk through an entire expected profit calculation at the aggregate model level, in the process computing these probabilities. First, a training portion of a dataset is taken as input by an induction algorithm, which produces the model that we will evaluate. That model is then applied to a holdout test portion of the data, and the counts for the different cells of the confusion matrix are tallied. Finally, we use multiplication and summation to get the expected value. Let's consider a concrete example of a classifier confusion matrix. Error rates. When calculating expected values for a business problem, the analyst is often faced with the question, where do these probabilities actually come from? When evaluating a model on testing data, the answer is straightforward. These probabilities, of errors and correct decisions, can be estimated from the tallies in the confusion matrix by computing the rates of the errors and correct decisions. For example, if we had 100 data points and 40 true positives, which would be listed in the confusion matrix, then the probability of a true positive is 40%. Costs and benefits. To compute expected profit, we also need the cost and benefit values that go with each pair, showing the predicted and actual outcomes. These will form the entries of a cost-benefit matrix with the same dimensions, rows and columns, as the confusion matrix. However, the cost-benefit matrix specifies, for each predicted actual pair, the cost or benefit of making such a decision. While the probabilities can be estimated from the data, the costs and benefits often cannot. they generally depend on external information provided via analysis of the consequences of decisions in the context of the specific business problem.